Hello everybody. So recently I was doing some research on the different attributes of a shader inside Maya, and I realized that if I understand how the light behaves in 3D and how the render engines work with the light photons, then it's much easier to play with the shader's attributes and get the exact result that I'm looking for. I realized that it will also help me debugging a lighting scene and even optimizing the renders. So we all know that when we are rendering a scene, the render engine simulates photons emitted from lights reaching to a surface, having some predictable or unpredictable behavior, and eventually ending up on the camera. The combination of all of these millions of photons on the camera sensor forms the rendered image. However, I realized that sometimes this simplified diagram might not be that much descriptive, so I decided to actually get into Maya and visually show the behavior of the light photons hitting a surface in 3D space. So before getting into Maya, as you can see, I mean, we already know that whenever we are having a light in a scene, the light source emits some lights, some photons that we call them incident light. And these photons only have a couple options. They either can be reflected, they can get into the skin of the surface, do some very small scattering on or in the skin of the surface, and then bounce off of it. And these are called diffuse, or these are the ones that actually form the base color of the object. Some of the other rays might be able to actually pass the upper layer of the surface and get into that and do some more of those scattering under the skin of the surface and then come out of the object, and these are called subsurface scattering. And some of them also have another option, which is being able to get into the object, being refracted in the object, and then passing through the object. So for each one of them, we have a separate name. These are the reflection rays, these are the diffuse rays, the subsurface scattering, and the transmission or refraction rays that we can have for any given material. For the sake of this tutorial, I used Arnold's new aiStandardSurface shader, which is, I think, from Arnold's version 5 and above. So I used Arnold's aiStandardSurface shader. However, the concept is all the same. I just wanted to have a shader so I can play with its attributes and parameters to be able to show or visualize all of these different light behaviors within the 3D space. So let's dig into Maya and see what I have there. I actually created a very complex rig which I created for this tutorial, and I'm going to show you how it works actually. So I'm having this red arrow here which is representing the incident light. I'm gonna just pull it over a little bit so we can see what's going on here. As I said, I'm using aiStandardSurface shader inside Arnold, and for that shader I'm having all of those four options that I can have for any given light inside a 3D space. So I'm going to go over each one of these parameters. The first one, which is the simplest one, is the base attribute, which actually controls the base color or the diffuse color of the material. So any color that you choose for the base color is actually going to form the overall color of your material. So for example, if I pick a very light green or blue for my base color, you can see that this is actually because of these diffused photons that are able to get under the skin of the geometry and then come back to our eyes. So that's the easiest one. I mean, you will choose the weight of the diffuse, and as you can see, the more I put for the weight of the base color, the more of these light rays I'm gonna have on the surface of the object. All right, so let's turn it back to 0 and see what else we have. The next attribute is called the specular, which is actually the photons that are able to being bounced off of the surface without getting into the object. So if I increase the weight of the specular attribute here, you can see that I immediately can see the reflected light ray here, and it's also obeying the physics law here, which is any reflected photon is actually being reflected in an angle that is equal to the angle of the incident light ray. So everything here is actually connected. And also we have another color slider here for the specular attribute, which defines the color of these photons that are being bounced off of the surface. So if I want to, for example, create a non-conductive material, I will choose a color of white, which is, for example, for plastics, stones, woods, and all of these types of materials. They're going to have a white color for their specular or reflected light rays. I'm going to get back to these parameters later on. I'm going to just move on to the transmission and subsurface scattering. I will come back here because I want to just quickly go over each one of these 4 options that we have for any given material. So I'm going to turn back the specularity to 0. And I'm going to talk about the transmission. So the name of the attribute actually describes what it does. The transmission attribute defines how many and how much of these light photons are able to pass through the object and reach to the other side of it. So as you can see, as soon as I start giving it a weight, I can see at least one light ray being able to pass through the object and coming out of it on the other side. And again, it's all connected, so if I want to play with that, you can see the result here. Depending on the angle of this incident light ray, we will get different results. All right. And I'm going to again move on because we have more options here, more attributes here that we can play with. But for now, I'm going to just move on to subsurface scattering and just just talk about the basics of the attribute. So I'm going to go back and get the weight of the transmission back to 0. And I'm gonna bring up the subsurface scattering attribute here. So again, the subsurface scattering is the attribute that defines how much light rays or how much photons are able to get deeper into the object, do some random scattering, and then come out of it. So this is defined by the subsurface scattering. And the more of the weight I have for subsurface scattering, the more photons are able to get into the object. Just as we are on the subsurface scattering topic here, I wanted to also talk about something else. Usually when you're dealing with subsurface scattering attribute and you want to do a quick render or do the final render for your object, you will realize that you will get a very, very noisy result when you hit render. That's because of the way the subsurface scattering actually works. As you can see right now, I'm having 300 curves here that represent 300 photons, I will say. As you can see, since they are having some very random scattering effects, random movements inside the object, and they are actually lighting up the whole surface of the object, we will have some lacking in terms of the number of photons that we need here. And in order to fix that, that's the only reason we are getting that noisy result when we are using the default values for subsurface scattering. So in order to solve that, there is a place that you should go to actually fix that. So if I bring up the render settings, here's my render settings, and in the Arnold tab, there is a sampling tab for the subsurface scattering. Right now, as you can see, that by default it's set to 2. Maybe for diffuse or specularity, having 2 samples might be enough, but just because of the fact that subsurface scattering is trying to emit all of these photons inside the object and they scatter all around the place, they're going to be too diffuse, too faded. So definitely we need to have more subsurface scattering samples. So I would say sometimes when you start rendering your scene with subsurface scattering materials, the only way that you can fix the noisy subsurface scattering result is here. This is the attribute that you can play with. You can increase it, and you should be careful about not increasing it crazily. But this is the place that you can fix or make some softer result or less noisy result for your subsurface scattering materials. All right. So I just wanted to point that out. So I'm going to dial the subsurface scattering back to 0 and go up to the specularity. So I'm going to go back and increase the specularity weight up to 1, and I'm going to make a good looking light angle here. And then here you can see that we also have an attribute called roughness, which actually defines how rough your surface is. So just to show you simply how this roughness behaves or what does it do to your object, I'm gonna dial down the specular weight to 0 so we can just focus on the surface of the object. And I'm going to increase the roughness attribute here. So this is actually, the roughness attribute is actually introducing some microsurfaces on the surface of your object. So this roughness is actually just under the hood, behind the scenes, is going to displace your geometry with some microsurfaces that you can define. And it will say that this surface is not a very perfect surface, but it's a surface that has some microsurfaces, which means that, for example, if I increase the specularity weight, you will see what happens. So all of these reflected light photons now are in random directions depending on how rough the surface is. They will be reflected in random directions, right? As opposed to when we had a roughness of 0. You will see that the less roughness we have here, the less random will be these reflected photons, until to a point that we put the roughness back to 0 and we will see just one light ray which is reflected in just one direction. So that's the cool thing. I mean, you can introduce some roughness for your material by increasing the roughness attribute here, and the result would be, whenever you are having a roughness introduced for a surface, the result would be a very blurry highlight on your surface. So if your surface is having a 100% specularity, you can also see something here. As I increase or decrease the roughness here, you will see that the highlight gets more blurry, and or maybe if I decrease the roughness back to 0, you will see the highlight is actually very pointy. That's only because of those microsurfaces. Also, another important thing is that just because of the concept of energy conservation, whenever we introduce some roughness to our specularity, you will see that the intensity of the highlight actually gets lower. That's because the amount of the light photons are still the same. We are not changing the number of the reflected photons. We are just saying that not all of them are in one direction. So for that reason, when we introduce the roughness, not only it will blur out the highlight, but also it will decrease the intensity of it for any given point on the surface of the object. But overall, we are having the same amount of photons with the same amount of overall energy for all of the specular photons. All right, so that was one thing. Also, while we are on the concept of roughness for this given material, I wanted to also talk about another term which is called anisotropy. So right now, again, all of these light rays, all of these reflected light rays are in random directions. I mean, they are still following the rule of having the same angle with the incident angle. I mean, if I change the angle of the incident light, you can see that overall they are following the same rule. However, just because of those microsurfaces, we are having some blurred highlights on this surface. So let's go back and see what the anisotropy attribute does. I'm gonna again bring back the specular weight back to 0 so we can just focus on the object. So again, it's all about the microsurfaces. Previously, all of these microsurfaces were all randomly in random directions. However, if we are dealing with some material, some objects that are, for example, brushed aluminum, we know that we do have these microsurfaces, though they are all sort of in one direction, which means that, for example, if I increase the anisotropy attribute here, you will see that those microsurfaces still exist. However, they are all in this direction, right? What does it do actually? So still we are going to have a sort of rough specular effect or specular highlight on the surface, which has this anisotropy effect or anisotropy attribute activated for that. However, look what happens if I increase the weight of these light rays. Right now you can see that even though they are all randomly in different directions, still they are actually on one plane. So that's only because these microsurfaces are actually in one direction. So that will cause a sort of brushed metal kind of look for your material. So if I bring down the anisotropy a little bit back, So it's not that harsh. You can see a very simple result of it here on this sphere here. That's only because by introducing the anisotropy, I'm actually saying that all of these macro surfaces are in one direction. And since we are on the same page, the anisotropy, you also have another attribute which is called rotation, which just practically rotates the direction of these microsurfaces. So now they are all vertical, and it will make these reflected light rays to be random directions, but again on the same plane in another direction. So this is how it actually works under the hood. All right, so I'm gonna bring back the roughness to 0, bring back the weight of the specularity to 0, and I'm going to talk a little bit more about transmission and subsurface scattering. So I'm going to bring back the transmission, and another thing that I wanted to talk about is, first of all, the color of the transmission or the transmitted photons, which actually just defines the color of these photons that actually are able to pass through the object. So this is the place that you can change this color. So I'm going to, for example, change it to blue or maybe darker blue, and you can see the result is actually like that. So I'm going to bring it back to yellow. So for transmission, we also have another attribute which is called scatter, which is practically doing the same thing as the roughness here. However, this scatter is something that is dealing with the microparticles inside the object. So sometimes you want to show an object that has some transmission effect on it. However, it's not that glassy. Which means that the photons are able to pass through it. However, just because of those microparticles inside it, these photons are going to be scattered a little bit within the volume of the object. So if I introduce some scattering for this material, look what happens. These light rays are able to transmit through the surface. However, they're all a little bit randomly scattered in different directions inside the object. This actually causes the look of any object that is behind this surface to be a little bit blurry. And talking about having the look of the object behind the surface to be distorted, we also have another parameter that we can control, which is called IOR, which is actually index of refraction, which will define the type of the material that you are trying to create. So for example, if we have a water material here, the index of refraction is something close to, I think, 1.305 if I'm not wrong. So it means that the more IOR you introduce, the more bend will happen on these transmitted light rays or refracted light rays. I'm gonna bring back the scatter to 0 so we can just focus on one of these light rays. So just because I increase the index of refraction here, I'm saying that these light rays are actually bent more inside the object. So whenever a light ray is able to get into this object, just because its speed is going to be changed within this object compared to the material that we have around this object, which for this case is, for example, air, the light rays are going to be bent a little bit down. And this is the place that you can define this bend actually, and how it will react or how it will work with your light photons. So I wanted to also talk about index of refraction here. All right, so let's go back. I also wanted to show you this as soon as I introduce a scattering parameter here. Again, if I decrease the transmission weight here, you can see that not only I'm decreasing the size of these light rays, which is a representation of lowering the weight or lowering the intensity of these transmitted photons. Not only I'm changing the size of them, but also I'm having less and less of them. So I just wanted to show how this weight actually works. All right. So the last one is the subsurface scattering, which is a little bit more complex. So I wanted to spend some time to show how it works, at least on the aiStandardSurface shader. But again, the concept is the same for any other material, for any other render engine. So I'm going to introduce the weight or I'm going to bring up the weight for subsurface scattering, and I want to show you what happens when we play with these attributes here. So for aiStandardSurface shader, we are having a subsurface color and radius and then a scale. I've seen some people immediately when they wanted to play with the subsurface scattering effect, they think that this is the place that they can choose the color for subsurface scattering, which is not correct. This is not the place that you will define the color of subsurface scattering. Subsurface scattering actually happens just around the edges of the object where we are having very thin areas on that object. So if you change the subsurface color here, this is something else. This is actually the base color. So sometimes when you want to create an object that is all subsurface scattering, you can just ignore the base color and you can define your base color here. So this is actually what the base color does. However, the place that you will define the color of the subsurface scattering effect is on the radius. So let's see how it works. First of all, you can see that the radius here is not an attribute. You might say radius is just a number. So why are we having this color slider here? That's because they wanted to just combine all of the attributes in just one slider. So let's see how it works. If I click on this radius color slider, you will see that it will bring up the color picker, and if I switch to RGB values, you can immediately see that I can define the color that I want for the subsurface scattering effect. And how it works is in a way that if you want to, for example, have a subsurface scattering color equal to red, you can zero out these values for green and blue, all right, and it will give you only red light rays. The way subsurface scattering works is that by the radius you are saying that among all those photons that are able to get into this object, only the photons that are having a wavelength of red color are able to get into this object. The rest of them are not able to get into the object. So just because I've put 0 for green and blue values here, I'm just saying that the blue and green light photons, just because of their wavelength, are not able to get into this object. So this red color here is defining which color channel I want to be able to see for the subsurface scattering. However, it also does something else. If I want to increase or decrease the effect of subsurface scattering for the red photons, I can simply play with this attribute, and let's just say what happens. So I'm going to choose this slider just for the red channel, and as soon as I decrease the red value here, this is the red value, I'm decreasing the red value. Just look at here. So as soon as I decrease the value for the red channel, you can see that I'm not only getting rid of some of these light rays or photons, I'm also changing the radius here. So that's why it's called radius. So not only I'm decreasing the number of the photons here for the red channel, but also I'm saying that these photons are able to get into this object less and less. So I'm changing the radius of this penetration, right? And again, I can even introduce some green photons here. So as soon as I introduce some green values for the subsurface scattering radius, you can see that I'm increasing the number of photons, which means that I'm increasing the number or the value of the green color here, and saying that I want to have them to get more deep inside this object. Okay, same as the blue channel. This is how subsurface scattering works. I'm gonna type in maybe 0.7 for green and 0.2 for blue. And I wanted to also talk about another attribute here, which is called scale. So usually when you are not getting a good result for your subsurface scattering, you will immediately start playing with the scale value. But if you don't know how it works, you are actually going to be lost inside your render. Here's the point. Subsurface scattering is actually very dependent on the scale of your scene and the size of your objects. If you are not creating your objects in real world scale, it means that your subsurface scattering is not going to act perfectly. So in order to be able to overall change your scale or change the scale of your scene, or saying that, for example, this sphere here is not 1 meter but it's 1 centimeter, you can change the scale to something like 100 or maybe 0.01. So this is an overall scale, overall multiplier that will multiply whatever you have inside the radius values for the red, green, and blue values here, it will multiply them to this number, and it will give you a very different result for your subsurface scattering. So you should be careful about playing with this scale value here. And as you can see, it will change how deep your light rays are able to get into this object. Again, it's an overall multiplier, which means that if you, for example, have a 0 value for your green photons, still you're not gonna have any green values even if you scale up your subsurface scattering effect. And usually the way I work is that I will first I want to see the effect of subsurface scattering, so I will just choose a very bright color for my subsurface color, something like white, and then I will play with the radius for different channels for my subsurface scattering. And when I'm happy with the result, if I want to have a base color for my subsurface scattering, or if I want to have a base color for my object, I will introduce the color here with this subsurface color. All right, that's about it. So I just wanted to show you this rig that is actually working with AI standard shader. But again, all of these concepts are actually applicable to any other engine that you're using, any other type of material that you can create within your scene.